The architecture of any Asian noodle represents a profound, precise synthesis of biochemistry, thermodynamics, and structural engineering. We can categorize the vast noodle landscape of the Asian continent into 12 distinct specimens, each defined by its specific botanical origin. This entire architectural landscape splits into two primary phylogenetic branches. The divide separates structures bound by highly cross-linked protein networks from those bound exclusively by the thermodynamic melting and recrystallization of starch polysaccharides. Predicting how a noodle behaves under thermal and mechanical stress depends entirely on mastering the physics of this microscopic divide. In the gluten matrix family, mechanical shear forces the endogenous gliadin and glutenin proteins in wheat flour to crosslink. This creates a continuous structural scaffolding. Confocal microscopy reveals a rigid, three-dimensional protein honeycomb. In its raw state, this network acts as a secure cage for dormant starch granules. During boiling, these granules swell exponentially. The surrounding protein network must stretch and contain the rupture to maintain the noodle's integrity. The strength of this network changes with its chemistry. Sodium chloride in udon tightens the network by shielding electrostatic charges, while ramen requires a much harsher chemical environment. Introducing kansui, a caustic alkaline solution, pushes the dough to a pH between 9 and 11. This triggers a chromophoric shift in the flour's flavonoid pigments, turning the dough neon yellow. This alkalinity forces the rapid deprotonation of sulfide hydryl functional groups, oxidizing them into rigid covalent disulfide bonds. These disulfide bonds act as immovable molecular spot welds. They create a tightly cross-linked gluten matrix that resists boiling broths. Ramen architecture is further classified by its hydration level. A low ratio of 25 to 30% yields a brittle matrix, which uses capillary action to rapidly absorb fat emulsified broths. However, exceeding a 2.0% kansui concentration causes runaway alkaline degradation. The amino acids within the wheat proteins break down, producing methanes and a pungent ammonia gas. The snappy resilience of a premium ramen noodle results from the artificial manipulation of the protein's oxidation state through extreme alkaline chemistry. Across the biomolecular divide, industrial rice noodle production requires high amylose indica rice to prevent the structure from collapsing. Structural integrity here relies on starch gelatinization. Under thermal kinetic energy, semi-crystalline raw granules absorb water and distend violently. Different processing methods yield different architectures. Flat pho noodles are steamed and rapidly cooled, while round bun noodles undergo a lactic acid fermentation that alters how the starch swells. Southern Vietnamese hủ tiaus utilizes a specific chemical modification, incorporating refined tapioca starch at a strict 25 to 30% ratio. The highly branched amylopectin molecules in tapioca physically disrupt the rigid crystallization of the rice amylose. These branched molecules act as internal shock absorbers. They allow the matrix to compress and rebound, creating the elastic bounce known as die. When a broth-based rice noodle fails, it shatters and disintegrates into a mushy paste. This collapse is the result of a severe amylose deficit. Without a linear polymer scaffold, the starch granules absorb water uncontrollably until they rupture, spilling their contents into the broth. A rice noodle matrix inevitably dissolves under thermal stress if it lacks a sufficient volume of linear amylose polymers to build a rigid scaffolding. The pure extracted starch family bypasses whole grains to form glass or cellophane noodles from isolated starch matrices.
Mung bean starch, which is exceptionally high in amylose, creates a dense and perfectly transparent gel network as it cools. Mung bean remains thermodynamically stable, unlike sweet potato starch noodles, which contain a higher ratio of branched amylopectin. Under a simulated scanning electron microscope, the mung bean matrix appears smooth and continuous. The sweet potato matrix is jagged, with numerous cavernous air spaces. This porous architecture allows the sweet potato noodle to function as a culinary sponge, deeply absorbing heavy braising liquids. These delicate glass noodle matrices are susceptible to a complete structural breakdown known as syneresis. In cold environments, the crystalline polymer regions contract violently. This reorganization physically squeezes the bound interstitial water completely out of the gel matrix. The extreme translucency and gelatinous chew of glass noodles result in a matrix that remains unstable at freezing temperatures. Buckwheat serves as a botanical outlier. As a pseudo-cereal, it contains no gluten, presenting a significant structural deficit for noodle formation. The Ni-hachi ratio solves this by introducing 20% wheat flour, the exact minimum mass of gluten required to bind the granular buckwheat together. 100% buckwheat Juwari soba represents the limits of non-gluten engineering, relying instead on precise thermal manipulation. By pouring boiling water directly into the raw flour, the artisan prematurely gelatinizes a fraction of the buckwheat starch. This localized gel acts as the sole biological glue for the dough. Beyond dough engineering, we can analyze the extreme thermal kinetics of wok frying at temperatures exceeding 200 degrees Celsius. When moist noodles violently hit the scorching pan, the surface moisture flashes instantly into a vaporous, high-pressure steam. This creates a microscopic high-pressure zone, known as the Leidenfrost effect, which repels the cooking oil while simultaneously steam cooking the noodle's interior. Simultaneously, the intense heat triggers a cascade of non-enzymatic browning called the Maillard reaction. Nucleophilic amino groups from the structural proteins react with carbonyl groups to generate the volatile organic compounds that define the smoky aroma of wok hei. Traditional wok frying executes a violent, highly calibrated physical phase transition and a complex chemical reaction simultaneously. Executing Asian noodles at a professional level relies on verifiable physics over subjective culinary dogma. The practice of adding oil to boiling water to prevent sticking fails against the laws of fluid density. The lipid molecules float at the surface, failing to interact with the hydrophilic noodles submerged beneath them. The common belief that adding salt makes water boil faster contradicts a core thermodynamic principle known as the ebullioscopic constant. In culinary quantities, the resulting boiling point elevation is practically insignificant. Failing to rinse Asian noodles results in a physical failure known as uncontrolled surface gelatinization. Rinsing in ice-cold water instantly halts carryover thermal momentum and mechanically strips away the sticky exterior amylose gel, preventing the strands from welding together. The glossy structure of Isdal noodles is a result of industrial flash frying, not a coating of synthetic wax. Submerging the dough in 150-degree oil evaporates the internal water, creating thousands of microscopic capillary voids. These microtunnels rapidly draw hot water into the core to re-gelatinize the starch matrix. Mastery over the Asian noodle spectrum relies on the deliberate, encyclopedic manipulation of biopolymers under extreme thermal stress.